Physics chapter 29 theory video 3. Write down the rest of the note. So this Einstein's E equals mc squared equation can be written as delta E equals delta mc squared, or E equals c squared delta m, E equals mc squared. So the reason why we put delta E is because we are talking about the change in energy and change in mass. So this write down underneath that, right? The mass of the system increases when energy is applied to it, and the mass of the system decreases when energy is released from it, according to this equation. So this is the mass defect scenario. I don't think it is required for you to write down this example, but write this down. When protons and neutrons combine together to form a nucleus, it will lose a very small amount of energy, within brackets mass, and this loss of mass is known as mass defect. I hope you understood. So now we have to discuss mass energy conservation. Einstein pointed out that delta E equals delta mc squared applies to all energy changes, not just nuclear processes. If it is a chemical change, it will still follow this equation. We start off now, for example, if in burning carbon, we start off with carbon and oxygen, then we have carbon dioxide and energy. If we take the mass of the carbon dioxide, it would be a little less than the mass of the carbon oxygen at the start of the experiment. Because the total potential energy is going to be less than that of the start of the experiment. So therefore the mass is lesser. Because these changes in mass would be very less, that is, if we take 1 kilogram of carbon and oxygen, it would be less than microgram. So if we take 1 kilogram of uranium, we will have a different relationship. So that is actually something that we are going to discuss later on. So in a chemical reaction, it is quite less. The change in mass is going to be very less. So that is because the energy that is lost is very small. So you would have an idea. In a nuclear fusion or a fission reaction, you would have a high loss of energy. So you would you can expect the mass change also to be high. So before we go on to the next part, I want you to do question number 3 and 4. Write down this note, 3, 4 and 5 rather. Write this note down. This Einstein's mass energy equation applies to all energy changes. That is, even in chemical reactions, when there is a change in potential energy, the mass would also change. Please do question number 3, 4 and 5, and if you have any questions, you can ask. After doing those questions, write this, listen to this. Another unit of mass. Now we know that energy is equal to mass. So we can take delta E equals delta mc squared. So we know the mass is in kilograms. So that is the SI unit of mass. But we can take the nucleus of nucleus, because it is very small in kilograms, it is easier for us to understand if there is another smaller unit. We take this as the atomic mass unit, which is the symbol U. The conversion factor of atomic mass unit is 1 U equals 1.660538921 into 10 to the power minus 27 kilograms. So what we do is, if we want to convert from atomic mass unit U to kilograms, we multiply it by 1.6605 into 10 to the power minus 27. So proton, it would have the symbol 1p, and its atomic mass unit is 1.007276. This you can see in all of these things, the nucleon number they have in proton, it is 1, neutron 1, helium 4, carbon 12, potassium 40, uranium 235. If you take a close look at this, you will see the atomic mass unit of each of them are going to be very close to the nucleon number. But in carbon 12, it is precisely 12, because that is actually the basis that we take. I hope you understood this, and this is something that we have discussed earlier as well. So but do question number 6 and 7 also. Before we move on to the next part, write down a small note of this. Because calculating in kilograms is not easy, we use a smaller unit, atomic mass unit, within brackets U, where 1 U equals 1.66053891 into 10 to the power minus 27 kilograms. Put a star and write down to convert U to kilogram, multiply by 1.6605 into 10 to the power minus 27. And write down this table 29.3, that will make more sense to you. Now we are going to discuss about energy released in radioactive decay. We know that unstable nuclei would emit alpha, beta and gamma radiation, or alpha beta particles with large amount of kinetic energy. Then we use this Einstein's mass energy equation, delta E delta mc squared, to figure out from where this energy is going to come from. For example, if we take a nucleus of uranium 238, 238 is a mass number, remember that. So it decays by emitting alpha particles and turns into an isotope of thorium. So U23892 turns into thorium 23490 plus alpha particle, that is the helium nucleus. So this uranium nucleus is going to be a highly unreactive, unstable, high energy, unstable state. So when it goes through this decay process, the thorium is going to be more stable and a lower energy state. So that means there should be a decrease in the mass of the system. So we know that the combined mass of the thorium nucleus and the alpha particle is going to be less than the mass of the uranium nucleus. So that is based on Einstein's mass energy equation. We can find out that the difference in the mass is what has caused the energy, or the energy released is equal to the difference in mass. So if you take the most accurate values, we will get something like this. mass of 238 uranium nucleus is they have given the value. Then alpha particle nucleus of thorium nucleus and the alpha particle would be that. Then the change of mass would be minus 7 into 10 to the power minus 30 kilograms. Minus means there is a decrease in mass, so as a result energy is released in this decay process. So the energy released is 6.3 into 10 to the power minus 13 joules by using delta E equals delta mc squared. So this is a single atom. If you take 1 mole of uranium, that is 6.02 into 10 to the power 23 nuclei, that would have the potential to emit 10 to the power 11 joules. That is a whole big amount of energy. So we can use the same principle to figure out how much energy is released in a decay reaction, whether it is alpha or beta decay. Let's write down a note on this. Energy released in radioactive decay is the topic. Unstable nuclei will emit alpha and beta particles of large amount of kinetic energy when they decay. In the following example, a high energy unstable uranium isotope decays to produce a low energy, high stable thorium nucleus. In the earlier note, I might have, I'm not really sure what I gave, but the uranium is high energy, low stable. Thorium is high stable, low energy. Then continue writing along with an alpha particle within brackets helium nucleus. During this decay, the change in mass would be equal to the energy released. Take your textbook and write down this calculation the way they have done it. That would be useful for you. This part, write it down. If you have any doubts, please ask. And once you have done it, you would be able to use the equations to figure out the amount of energies that have been released. Please do question number 8 as well.